At this point, we have seen how the model receives an input, converts that into an input embedding, and we affect it by adding positional encoding. So we are ready to go into the transformer. The first sublayer that the transformer has is the attention layer. The attention mechanism in the transformer is used in three parts. In the encoder at the beginning, and then in the decoder we have it in two places. Again, at the beginning and following the previous attention module. But they are different applications of the attention module. One is called the self-attention module. The one here is called the masked attention module, and the one in the decoder after this masked attention module is called the cross attention module. The attention mechanism is what I call the heart of the transformer, or maybe the brains. Self-attention allows the model to weigh the importance of different words in a sentence. It is a process where the model looks at other parts of the input sequence to better encode a specific part of that sequence. In essence, each word gets a chance to attend to all other words. This mechanism is what gives the transformer its ability to understand contexts and relationships in the data. The attention mechanism starts with the creation of three matrices: query, key, and value. These three components are like different roles in a conversation. One example that I use a lot to explain this in other terms is this. Imagine that you open your Google search, and in the search bar you enter something that you are looking for. This is the query. For instance, flowers shops around me. This will be the query. When I hit enter, Google will give me a list of results. This list of results is ordered by relevance, and these are the keys. Each item in this list is telling me how it is related to my query of flowers shops around me. Then we pick one of the entries in the list to see the details. The information provided when we click in a link is like the value. This is the content or the message to our query. So again, we have the query, the key, and the value. Let's see these three components and the above explanation now in the scale dot product attention formula. First, we have the dot product. When we do the dot product between the query and the key, we are trying to find the words that are more relevant to each other. For my own intuition, I equate this to cosine similarity. It is not exactly that, but this allows me to gain some understanding of what is being accomplished here. Then in the formula, we scale down the dot product of the query and the key. Why? Because when the numbers are too big, they can mess up the model's ability to learn smoothly. It's like turning down the volume to hear better in a noisy room. Finally, we apply softmax to convert the previous result into probabilities for each word. These probabilities will tell the model how much attention to pay to each word in the sentence. Continuing with my personal representation, at this point, the way I see it is like I have created almost a Boolean filter that we will use in an image processing to highlight important areas. Just to clarify, it is not really Boolean, as I have values that range from 0 to 1. But the main idea to gain intuition is that the result of the softmax can be seen like a filter that we will apply in top of the values to highlight important features. The result of the softmax is known as the attention scores. Finally, we take the attention scores and we do one more matrix multiplication with the value. Continuing with the analogy of the filter and the image, we are putting the filter in top of the image to highlight the most important features and hide the least important ones. The resulting matrix from this multiplication of the attention scores and the value is a weighted representation of the input sequence, where each word's representation is influenced by the attention paid to all other words. So how is this attention formula implemented? We will create a function called the scale.productAttention that will receive query, key, and value. Then we will calculate the scores by multiplying query and the key transposed. And after that multiplication, we will divide it by the square root of the dim k that we calculated previously. Once you have the calculation of the dot product and it is scaled, you apply a softmax according to the formula, and the last step is to multiply the result of this operation with the values. We got the weights here after the softmax, and we do a matrix multiplication with the values, and that is what we return from this function. Going back to our diagram of the attention module, we can see that the components are the query, the key, and the value that then enter into the scale.productAttention box. All these components together can be referred to as an attention head. We saw how the attention module starts with what we called an attention head. In reality, the transformer implements many of these heads in the attention module, hence the name multi-head attention module. We start with the input embedding. As we saw, this will come into the attention module. Inside the attention module, we can define one or more attention heads. For example, we can create 4 attention heads. Each one of these attention heads will have as input a section of the input embedding. By doing this, we will have each attention head focus on different parts of the input to find specific features. After all these attention heads have processed their inputs, all the outputs of each attention head are concatenated and passed through a linear layer for an additional transformation to have as output the contextual embedding, which will have the exact dimension of the input embedding. Thanks to this multi-headed attention, the transformer is capable of capturing more complex relationships in the data. Again, each head focuses on a different part of the input sequence, allowing the model to attend to various aspects of the data in parallel. The typical example indicates that in a sentence, one head might focus on syntactic aspects, another on semantic aspects, and yet another on contextual nuances. In tasks like translation or summarization, different types of relationships like grammatical, thematic, or logical connections can be better captured and represented through multi-head attention. By having multiple views or interpretations of the same data, the model can develop a more comprehensive understanding. It's like getting multiple experts' opinions on a topic instead of a single one. The multi-head attention also helps the model capture relationships between words that are far apart in the input sequence. This is crucial in many natural language tasks where context and the order of words play a significant role. So, how is this multi-head attention model implemented? Let's see that in code. To implement the multi-head attention, we create a class called the multi-head attention. In the init function, we will take basically our parameters, embedding dimensions, and the number of attention heads that we want. In our example, we picked 4. We will calculate the dimension of each head, which will be the embedding dimensions divided by the number of heads. And this is very important. When you are creating a model, make sure that the size of the embedding is divisible by the number of heads. Otherwise, the model will give you an error. Once we have defined these variables, we instantiate the heads, and this is going to be basically a loop through the number of heads, instantiating the previous class that we had created called attention head. Then we need an output linear layer that we create of the dimension embed dim by embed dim. And in the forward, we will basically go through each one of the heads, calculate its result, and concatenate them into the context embeddings. Then we will apply the output linear layer, and we return the context embeddings. That's it. Now we have gone in detail through the entire attention mechanism. We explored the query, the key, and the value, how they are applied in the scale.product attention formula. Then we saw how the attention mechanism is actually implemented in multiple heads, and we reviewed the reasons why this multi-head approach is important for the model. The next sublayer in the encoder is called the feed-forward neural network.